Okay, welcome back everyone to the online seminar series on fractional calculus and related topics. Today's speaker is Professor Serena Dipierro from University of Western Australia. Serena Dipierro took her PhD in mathematical analysis at the International School for Advanced Studies, SISSA, Trieste in 2012. After postdoc positions at the Universidad de Chile and University of Edinburgh and a Humboldt Fellowship, she held permanent positions at the University of Melbourne and the Università di Milano. In August 2018, she moved to the University of Western Australia, where she is now Professor of Mathematics. She is a Fellow of the Australian Mathematical Society and Australian Mathematical Society Hannah Neumann Lecturer. She has obtained prestigious awards, including the Australian Mathematical Society Medal, the Mahoney Neumann Room Prize, the Bartolozzi Prize of the Italian Mathematical Union, the Christopher Hyder Medal of the Australian Academy of Science, and the prize of the Bulletin of the Brazilian Mathematical Society. It's our pleasure to hear a talk from her today about the Fractional Malmheden Theorem. Please, the floor is yours. You may begin your talk.
So thank you very much. First of all, thanks to the organizers, Arran and Pavan, for inviting me to give a talk in this series of talks on the fractional calculus. So I've decided today to talk a bit about this Malmheden Theorem and eventually the fractional version of it that we did more recently, which is somehow a kind of sort of a classical topic, or it is very, very much connected to classical topics like that we all know in PDEs. But it's probably not very well known. Okay, so the name of Malmheden is not probably very well known. It's not maybe a very famous mathematician. So Malmheden was basically a student of Ritz. And let me go to I have a bit of a bibliography here. Basically, he wrote this paper almost a century ago now, and so in 1934, in German. Of course, he was a German mathematician. And the title of this paper is basically, if I remember well, my German is one new solution to the Dirichlet problem in spherical domains. Okay, so he's basically looking at a classical Dirichlet problem in spherical domains. Okay, he's looking at balls essentially. And then this theorem that I will discuss has been somehow revisited in various forms. So there are, for instance, more recent works or papers on the topic, and basically we discovered it with Enrico while we were writing this book on PDEs, and then we had this idea of looking at the fractional version of it. Okay, so this is what we did also with Giovanni Giacomini, who at the time was a PhD student here. So this is more or less what I will be talking about. So the classical version, somehow things that are connected to the classical version, and then the fractional version of it, and what consequences it has. So let me start with something very simple, very basic, someone that everybody knows, which is the mean value theorem. Okay, so no need to pause because it's not a big surprise. So we all know that if we look at harmonic functions, they satisfy the mean value theorem. Okay, so they satisfy a mean value formula. So a formula that involves the average over, so it involves either spherical average or I'm sorry, or a volume average. Okay, so this is something that we all know. So for harmonic functions, we know that the mean value theorem is true. Fine. And now the question is, the main question that is connected to another kind of classical theorem, which is due to Kuran, is, does the mean value formula actually characterize the domain? So is it true that if I have a domain omega in which every harmonic function satisfies the mean value formula, then this domain is a ball? So does the mean value formula characterize the domain? So this is the question. And the answer has been given after some other, let's say, papers in this direction, where some additional assumptions on the domain were imposed by Kuran in 1972. And the answer is essentially yes. So if I have a domain omega, which is an open subset of Arran that contains the origin, and I suppose that for every harmonic function in omega, I have basically the mean value formula in omega now, then omega must be the ball. Okay, so this is the statement. And now I'm going to show you the proof, because I think so the proof is basically something that fits in one slide. Okay, maybe if you forget about a few little computations, but very simple computations. It fits in one slide. It's very simple, but it's very elegant. It's based on the fact that basically we can define some sort of modified Poisson kernel. Okay, so first of all, I suppose that B1 is contained in omega, so up to a dilation, and there exists a point in common on the boundary of B1 and the boundary of omega. Okay, and then I define this modified Poisson kernel that is somehow centered at the point y. And then here are the computations that I won't do, but basically one can check that this function is now harmonic outside of y. H of 0 is 0. Okay, this is very simple to see because H of 0 will give me -1 + 1. But also, if x is outside the B1, this term is positive, it's not negative. And so H is bigger or equal than 1. Okay, so these are the pieces of information that we need. So, because H is harmonic, I can employ the mean value formula for omega. Okay, so I know that H of 0 is 0, but on the other hand, by the mean value formula is equal to the average of H, of the function H over the domain omega. And now I split this integral into an integral over B1 and an integral outside omega minus B1. Okay, and now I know that, so this is still a harmonic function in B1. So I can employ the mean value formula in B1. So same thing, I have of course to multiply and divide by the Lebesgue measure of B1, and I get the Lebesgue measure of B1 times H of 0. And now H of 0 is 0 again, so I end up with something like this. And now the other thing that we haven't used that is that H is bigger or equal than 0 outside omega. Now I am outside omega, so this integral is actually larger than the integral of function 1 over omega minus B1, so the Lebesgue measure of omega set minus B1. So all in all, what I have is that this is bigger than the Lebesgue measure of omega minus B1, and maybe this is a type, should be the Lebesgue measure of omega, but this has to be smaller or equal than 0, which means basically that omega and B1 coincide up to a set of null measures. So omega must actually be the ball B1. So basically this proves Kuran theorem. So it's a very, I like this proof, it's very elegant, it's based on a simple idea. So pick basically the right function that you want to use in the mean value formula and then use it in a smart way. And so this is for the classical case. Okay, so let's try to move now to Malmheden theorem. So this is just to recall ourselves about the Poisson kernel of the ball. And why do I want to recall the Poisson kernel of the ball? Because we know that if I have a Dirichlet problem, so a classical Dirichlet problem with the Laplacian, so say Laplacian u equal to 0 in B1, with u equals some nice f on the boundary of B1, then the solution of this problem can be written explicitly using the Poisson kernel. Okay, so the solution is the integral over the boundary of my domain, which is B1, of the boundary datum f multiplied by the Poisson kernel of the ball in this case, which is exactly this one here. Okay, so we have a nice way of writing in a nice analytical way of writing the solution of the Poisson of the Dirichlet problem. And now Malmheden theorem provides a geometric argument to construct this solution. Okay, so the idea is, again, I start with my favorite problem, Laplacian of u equal to 0 in B1, with some boundary datum. Now, I will take a point P in the ball. I will have a picture in the next slide, so it's going to be easier to understand. But I have a point in the ball, and then I take an arbitrary line, a chord passing through P. And what I do, I take, so I look at this chord, and I look at the endpoints of the chord, okay? So the points of this line that intersect the boundary of B1. I can evaluate F at these 2 points, because F is defined on the boundary of B1. And I can take the linear function that interpolates these 2 values, okay? And of course, the choice of the chord is arbitrary. I can pick any direction. So I can do this for any direction. I can compute the average over of these values over all possible chords through P. And this procedure basically produces the harmonic function in the ball. So this is the idea. This is the idea. Now, let's do this mathematically. So I have a point P in B1. I pick a direction, and I look at these 2 endpoints that I will call for simplicity Q plus E and Q minus E. These are the intersection points between the straight line with direction E passing through P and the boundary of B1. That if I do some trigonometry, I can write explicitly. Okay, so Q plus is going to be P plus some radius times E in the direction E, and Q minus is going to be P plus R minus. Okay, eventually R minus is clearly negative if I'm going in the opposite direction. And doing some trigonometry, I can write explicitly what these R plus minus are. Okay, not particularly difficult. So this is my picture that I promised. At this point, I pick a direction. This is my Q plus, this is my Q minus. I look at F Q plus and F of Q minus, and I take the the affine function interpolating these 2 numbers. So that I call LE. Okay, so LE is the affine function on this line, P plus ER, such that I'm interpolating F of Q minus and F of Q plus. So I can write this explicitly again in this form. And then I evaluate it at P. Okay, so now I take S equal to 0, so I don't have basically this term. I end up with only the last 2 terms divided by R plus minus R minus. Remember that R plus is positive for me and R minus is negative. So the denominator is positive, never vanishes. It's not a problem. And then what I do this for any E, for any direction, and I average. And I define UP to be this average. And the Malmheden theorem says that this is now the solution of the Dirichlet problem. Okay, so it's a geometric way to construct the solution of the Dirichlet problem in the ball. Okay. Now, why have I jumped from the mean value formula to Malmheden theorem? Because Malmheden theorem contains the mean value formula as a special case. Okay, it's a sort of generalization of the mean value formula that allows me to write basically U at any point of the ball rather than just U at the center of the ball. So in particular, if I take P equal to 0, well, all these objects, so if you see D of E, P equal to 0, so D of E will boil down to 1, just 1. Same for R plus minus. And so Q plus and minus are just, so P 0 are just plus and minus E. Okay, so the LE, so this linear function evaluated at 0 is nothing but, R plus and R minus are 1, sorry, plus and minus 1, and Q minus and Q plus are simply E and minus E. And so here I have FE plus F evaluated minus C divided by 2. And so U of 0, if I use Malmheden theorem, is simply the average over the boundary of B1 of this object. And now I split the 2 terms, I do a simple change of variable, and I get exactly the mean value theorem. So U at 0 is nothing but the spherical average of the function U, which is F is the boundary datum, at this point. Okay, so this is exactly the mean value theorem. So the Malmheden theorem is some sort of generalization of the mean value theorem. It contains, as a particular case, the mean value theorem. So the proof of Malmheden theorem is also nice. It's basically, essentially, you have to do some computations, as it very often happens in mathematics, but you have to do them in some sort of clever way. First of all, you have to introduce, you have to understand this change of variable formula that I will not prove, but it's essentially, again, I mean, this is nothing but really a change of variable. Okay, so you're simply doing a change of variable, but then you need some smart ideas, let's say, coming from linear algebra, because when you compute the determinant of the Jacobian, you end up with something that is a bit complicated, that you can simplify, that you have to somehow be able to write in a kind of a smart way. But it's nothing but a change of variables, okay, computations in the end. And this is true for any continuous function g, okay, so that we will apply it for a specific function in our computation. Now, the idea is that, okay, if I can prove that the expression that I have for Malmheden theorem, the expression that I have for my function u, is nothing but the integral of the function f multiplied by the Poisson kernel, then this is going to be my solution, because I know that I can write the solution via the Poisson kernel. So if I manage to prove that this is exactly the integral of f multiplied by the Poisson kernel, I'm done. That is the solution of the problem. So this is the computations that one has to do. So one writes u of p as using the Malmheden formula. Okay, so we do reverse engineering. We go backward, and we check that we somehow recover the Poisson kernel there. So we split these two integrals. These are essentially, if I swap e with minus c, these are essentially the same. And then I do some other direct computations. Again, you have to recognize things, so you have to be a bit smart. It's not completely trivia, but computations that one can do. So one recognizes that this object is equal to this object here, and then p minus q minus is minus r minus. And then if one plugs this information in the formula, one ends up with something like this. And then here, so you see, I keep the numerator here, the denominator here, and I multiply and divide by the same quantity. It's exactly the same quantity, because I want to go towards the Poisson kernel, okay? And now this function here is what is going to be my f, my g. Okay, g of e is this one. And now here I recognize g, evaluate the q minus e times something. And this is exactly what I had in my change of variable formula. So this is nothing but the integral of g of e. And now I write again what g of e is. And this is exactly f multiplied by the Poisson kernel. And so you must be the solution of my problem. Okay. There is a nice particular case, which is when we are in dimension 2. Okay, so when we are in dimension 2, something special happens. So we slightly change the notation now. We have again a point P in B1, but we don't look at Q plus and Q minus. We say that, okay, for every point Y on the boundary of B1, we call Q basically the conjugate point on the ball with respect to P. That again, one can write explicitly. Okay. And so the theorem, the two-dimensional case, which is actually due to Schwarz, says that, okay, now if I write U of P as the average of F at Q of omega, so I pick a direction and I look, so this is Y, but I look at the conjugate, okay, so the conjugate with respect to P, and I average over all the direction, then I get again the solution of the dirichlet problem in the ball. So it's slightly different from Malmeden's theorem. This one is nice because it has a beautiful application if we want to determine basically the temperature of a plate. So imagine that I have a disk and I know the boundary temperature and I want to determine the temperature at a given point. So for instance, Suppose the boundary temperature along the boundary of the disk is kept to be equal to 1 along a given arc, and then 0 along the rest of the boundary. Okay, so and the question is, if the temperature is 1 along a given arc and 0 elsewhere on the circumference, can you tell me the temperature at the point P of the disk only using elementary geometry? Okay, so essentially using Schwarz's theorem. So this is the picture. We have this disk, we have a point P, say my temperature is kept to be equal to 1 over sigma, and I want to know the temperature at the point P. Recall that if I want to use now Schwarz's theorem, basically I'm going to use Schwarz's theorem with f to be equal to the characteristic function of sigma, because that's my boundary value, my boundary function, my boundary datum. But Schwarz's theorem tells me that I have to compute the characteristic function at q of omega. So I'm essentially looking at the conjugate arc, which is now sigma prime. Okay, so I want that somehow when I compute the characteristic function at the conjugate of sigma prime, that is equal to 1. So I have to look at sigma prime. So the answer is I project the arc to the focal point P, I obtain the conjugate arc, and then the temperature is exactly equal to, so what? Well, the characteristic function of sigma prime. So I have the length of sigma prime divided by the length of the circumference, which is 2 pi. Just using Schwarz's theorem with f equal to the characteristic function of sigma. So I'm using this result, which is really basically a geometric construction. I can tell you the temperature at a given point on the disk. And let me stress that this holds true only in the plane. Okay, so it's a variant of Malmheden that holds true only in the plane, because suppose by contradiction that for n bigger or equal than 3, I have Schwarz's theorem. Take, for instance, sigma to be the basically the boundary of B1 intersecting xn smaller than 0. Okay, so the lower spherical cap be the lower half sphere, sorry. And so f is again the characteristic function of sigma. So if we suppose that the Schwarz's theorem is true, then the function u of p would be given basically by the surface area of the spherical cap obtained by projecting sigma through the focal point P. Okay, and this function would be harmonic, but this cannot be true. So let's look at the picture. So now, okay, of course it's a two-dimensional picture. You have to imagine it in higher dimension. So suppose that my sigma is the lower, so the half circle here, the half ball in the lower half space. I want to compute the temperature, say at the point P, which is 0, 0, 0, 0, and then 1 minus epsilon in the nth direction, and then so I have to look basically. So you see these two red dashed lines tell me what is the conjugate arc with respect to my original arc. Okay. By dimensional analysis, okay, so UP would be epsilon to the n minus 1, okay, or by trigonometry if you like. And then, so if I compute the normal derivative of u at the point 0, 0, 0, 1, so this point, the top point here, this would be the limit of u evaluated at p minus minus u evaluated at this point. U evaluated at this point is 0, because I am outside of the arc. But u evaluated at p is epsilon to the n minus 1. So all in all, I get epsilon to the n minus 2. And when n is bigger or equal than 3, I get 0. Okay, so this counterexample holds true only when n is bigger or equal than 3. Because otherwise, we know Schwarz's theorem is true in dimension 2. But this is against Hopf lemma. So if this were 0, we would violate Hopf lemma. So the Schwarz's theorem cannot hold in higher dimension. Okay, and the Schwarz's theorem is again computations. So somehow you have to apply the change of variable formula in a smart way and somehow recognize the function obtained, the construction, so the function constructed using Malmheden theorem. So it's not a difficult computation. Okay, now the next part of the talk is dedicated to trying to understand what can be said in this context for the fractional Laplacian. Okay, so I'm going to tell you, first of all, what the fractional Laplacian is for me, so the definition that I use, and then we're going to give a look at the fractional version of Malmeden's theorem. So let me consider a nice function for you from Arran to R. So nice means for me that I don't want to bother, too much at this point telling the regularity needed to write the integral. So I want a function for which I can write the integral. And let me take s in between 0 and 1. So this is going to be what I will call my fractional parameter. And so I define the fractional Laplacian of a function u at the point x as this integral over Rn of this sort of incremental quotient, which, if you can see, is of order 2s. Okay, so I have a sort of second order object in the numerator, so 2u of x minus ux plus y minus u of x minus y, divided by a kernel, which for me is y to the n plus 2s, and n is the dimension, okay, of the space where I'm living. So this is some sort of incremental quotient of order 2s, okay, so when s is equal to 1, it's an incremental quotient of order 2, but it is somehow taken over all of integrated over all of Rn, okay, so it's a non-local operator, because if I want to compute the function u at a given point x, well, if I want to compute the Laplacian of the function u at a given point x, it's enough to know the value, the expression of the function around the point. Here, I need to know the value of the function, like the big picture. I need to know the function everywhere because I'm integrating over Rn. Of course, the points that are closer to x, like carry somehow, so are more important they carry more weight in the computation. Points that are far away are less important in the sense that the kernel decays, but it decays polynomially. Okay, so I still see this interaction with points far away. And okay, so this is the way I like to write it, because I don't need to write the principal value, because you see, if u is a nice infinity compactly supported function, this object would be easily it's easily seen that it would be integrable for large y, so say outside the given ball, say b1, because maybe u is bounded, so I can integrate 1 over y to the n plus 2s. But on the other hand, when y is small, if u is nice, the numerator is of order y squared, which in tandem with this denominator y to the n plus 2s would make the integral finite. Okay, so that's why we write it like this. So one can also somehow decouple things, desymmetrize the integral and write it in this way, like many people use this definition. But then it's not clear, so when s is bigger than 1/2, that this object, the integral is finite, because even for u is infinitely compactly supported, when say y is very close to x, the numerator would give you an x minus y to the power of 1. So you need to kill 2s. Okay, so this is true when s is smaller than 1/2. Otherwise, you have to use the principal value notation. So you have to somehow remove a small ball around x and exploit cancellations. Okay, another definition that makes it maybe more similar to the classical Laplacian is the one using the Fourier transform. So for me, this Matkalev is the Fourier transform. So the fractional Laplacian of u can be written as the anti-Fourier transform of the symbol, which is now xi to the 2s, so the norm of xi to the 2s, times the Fourier transform of u, which is very similar to what we have when s is equal to 1 for the Laplacian. And as I said, this is a non-local diffusive operator, and I'm stressing a lot this fact that when s is equal to 1, we somehow recover the Laplacian here, and also we have some sort of second order incremental quotient here, because one can check that when s goes to 1, if we suitably renormalize, multiply by the right constant the fractional Laplacian, it converges actually to the Laplacian. So that's why we call this a fractional Laplacian and a fractional parameter. Somehow we are taking power, like a fractional power of the Laplacian. And we write the minus Laplacian because I want somehow to have like a positive definite operator. Okay, there. So it's very similar to the Laplacian, and indeed there's the classical Laplacian, the fractional Laplacian tends to average out oscillations, because if you look at this object here, if I want a function whose fractional Laplacian is 0, say an s-harmonic function, I want this numerator to be not too big. Okay, so I don't want too many oscillations there. And this has to be, and again, I have to look at the big picture. So this, I don't want oscillations anywhere, okay? So for the classical Laplacian, you have a good regularity theory because the Laplacian doesn't like oscillation around the point. Here it's very similar. We can hope for a good regularity theory because this is also a nice operator that doesn't like oscillations, but everywhere, okay? So not only around the point, but everywhere. So as I was saying, differently from the classical Laplacian, the fractional Laplacian takes into account the global behavior of the function. So we need to somehow have a good control of what happens everywhere. Okay, so the first question is, can I have, for s-harmonic functions, a mean value theorem? And the answer is yes. So a function is s-harmonic in BR, B capital R, so say s-harmonic for me means, again, the fractional Laplacian is equal to 0 in BR, if and only if for every small r in between 0 and capital R, I can write u as 0 as some sort of integral. So there is a constant here, which makes it somehow an average. But the integral is now, so for the classical Laplacian, we used to have an integral over the boundary. Now the boundary datum must be replaced with, if you want, an exterior datum, because if I want to compute the fractional Laplacian even in a ball BR, I need to know the function everywhere, even outside. So for me, the boundary is not really a boundary anymore, it's an exterior. So the boundary, the integral over the boundary of the ball is replaced by the integral outside the ball. And then I have the exterior datum, which is my function u, but now I have to multiply by a kernel. Okay, so I have an additional kernel produced in the mean value theorem that essentially makes everything integrable. So if we want to rewrite it in a more similar way to the classical case, we call whatever is not u here d mu r, and we can interpret mu r as a probability measure on Arran minus BR and write the fractional mean value theorem for short in this way. So this is more similar, if you want, to the classical case. So u0 is an integral on the boundary, so on the exterior of the function u, with respect to a given probability measure. Okay. And what we proved with the Claudia Bucur and Enrico Valdinoci is that basically there is a non-local, a fractional version of Kuran theorem, because again the question is, does the mean value formula characterize balls? The answer is again a yes. So if I have, as you can imagine, if I have a domain omega, a bounded open set in Arran that contains the origin, and let me call little r the distance of 0 from the boundary of omega. Suppose that I have some sort of mean value formula. So suppose that I can write for all s-harmonic functions u in omega, u of 0 to be the formula that I have, then omega must be the ball BR. So if omega satisfies a fractional mean value property with respect to a suitable measure, then omega is necessarily a ball. Okay, so this is what we prove with Claudia. And of course, you may think that we are cheating a bit because somehow there is something that very much, I mean, hint to a ball, right? Because mu r, I mean, we have a radius here, so of course omega must be br, but it's not completely trivial. And also, if you want, I don't know how to say this, but I mean, it is also connected to a slightly different problem, which is the problem of no harmonic measures. So, can I find an harmonic measure on a given domain? Okay, so in general, you cannot expect something like this if you don't impose something on the measure here. Okay, so the measure there is essentially the measure that you expect to have for the mean value form. The proof of this is essentially the same spirit as the classical Kuran theorem. So you want to find a suitable function. Remember, we had the modified the Poisson kernel. So a suitable function that is a s-harmonic and that does the job of the modified Poisson kernel in the first case. So we argue again by contradiction. We assume that omega z minus br is not empty, so it has positive measure, and we pick a point in there. And actually, because omega is open, I can find a ball containing omega. And so I know that omega minus br is basically non-empty. So mu r, this is to say that mu r, the measure of omega minus br, is strictly positive. And now, in general, if u is s-harmonic and u of 0 is equal to 0, I can play the same game that Kuran did. So 0 is equal to this object, but now I use the mean value formula. So this is equal to the integral in the exterior of u in the mu r. I split omega in that is integral into whatever is in omega minus br and whatever is in br. I use the mean value formula in br here. U of 0 is 0. So I end up with minus this integral here. And now the game is trying to understand, trying to find a function u that gives us a contradiction. And the way we find a function u is we use this result that all functions are locally s-harmonic up to an epsilon, up to a small f. This is something that I won't take a deep dive into. I'm not sure if Enrico is going to talk about this result in his talk, but the idea is that essentially if I have a function, a given function, say defined in a ball, I want this function to be s-harmonic in this ball, or at least almost s-harmonic in this ball. Why can I actually, of course, I cannot do that for classical harmonic functions, right? If I have a given function, it can be very far away from being harmonic in the ball, and there is nothing that I can do to make it harmonic. But in a non-local setting, remember that the fractional Laplacian in the ball does see also the contributions coming from outside the ball. So if I'm given a function in a ball, I can somehow complete this function outside to make it s-harmonic or almost s-harmonic in the ball. Okay, so I will not give you like more details about this, but the idea is that somehow non-locality allows you to do that. So the non-local setting is in a sense richer than the classical one, because I can somehow say that locally all functions are almost s-harmonic. And now we use this result with say epsilon equal to r squared over 4. Now we have to pick a function that we want to approximate with this theorem. So say we take x squared, we take a reference domain BR with r equal to basically the diameter of omega. And so if I'm given f, I can find a function that is s-harmonic in BR that is close in a good, a decent norm, say the L infinity, the uniformly close with respect to r, to my original function f. And now my function is going to be u star, which is minus this f little r capital R x plus the value at 0. And then one checks that, so remember we had this term here, okay, so we want basically minus u to be bigger than something, okay, than something bigger than 0. So this is what we want to do. And now, so we write u star, we add and subtract things. We use the triangular inequality. We use the fact that we know f is x squared, and we use the approximation result to say that these two objects are both smaller than r squared over 4. So all in all, I have this. So if I am outside capital R, minus u star is bigger or equal than r squared over 2. So now I know that minus u star is bigger or equal than something. And so when I plug it into my integral, I obtain r squared over 2 times the measure of omega minus pr, which I know is strictly positive, and this gives me a contradiction. So the only thing that you have to check is that, okay, you were actually allowed to use u star as a test function in your equality, but you can, because u star is 0 is 0. That's the reason why we subtracted the value of 0. It is s-harmonic because it was constructed like that. And so basically you can get a contradiction with this result. Okay, so now we know everything about the fractional mean value formula. What about Malmheden? For Malmheden, so this is the result with Giovanni and Enrico. For Malmheden, we can again find the geometric argument to construct now s-harmonic functions in a ball given a boundary datum. So I have the ball B1, an s-harmonic function in B1, and now remember that I have to replace the boundary datum with an exterior datum. So I have to tell you what the function u is everywhere outside B1. So this is now the right setting for the Dirichlet problem. What do I do? Well, we essentially follow the classical construction. The only thing is that now the function will be not an integral over the boundary of the domain, it will be an integral outside. Okay, so basically we have to do this construction at every in every let's say ball with radius larger than 1, and then somehow integrate it against a given kernel. So basically the classical spherical averages are now replaced by weighted spherical averages, because now I will be doing this. I will basically do some I will pass basically to polar coordinates. So we look at the integral outside the ball as an integral over the sphere and an integral from 1 to plus infinity. So these classical spherical averages are replaced by weighted spherical averages. Remember that I have a kernel now in the mean value formula, and the geometric transformations now must be scaled, because if I'm doing this for every radius, I have somehow to scale the construction, okay, to look at this thing not just in B1 but at every radius, So that's the main difference. See, so now the notation is a bit cumbersome, but this is exactly what I'm doing. So I'm saying, okay, I define f of rho to be f of rho x. Okay, so I'm scaling now the exterior datum to be in B, say 1 over rho. Rho is going to be small, and then this is the affine function. This is the notation for the affine function that connects again f evaluated at the two endpoints, and this must be scaled because now I have to look at it at every scale. Okay, so it's a bit ugly to look at, but this is what we are doing. We are just rescaling this construction to have it in any ball for every radius. So this is exactly the same construction. And then remember that we will need the kernel, okay, to make everything integrable in the end, but this is there also in the mean value formula. So this is going to be our kernel. And so basically this is what we have. Okay, so we have again, we go to polar coordinates, so we write the integral outside B1 with polar coordinates. So I have an integral in rho from 1 to plus infinity. And then on the boundary, I do essentially the same construction that before, but I multiply by a kernel. Okay, so this is the affine function, rescaled. And this is the kernel that I have to integrate against. Then use the solution of the fractional Dirichlet problem in the ball. Okay, so it's essentially the same. And let me mention that when p is equal to 1, remember that we know how things become simpler in our notation. So the affine function is now nothing but the same thing that we had before, but scaled. So it's f of rho e plus f of minus rho e. So and the kernel also simplifies a bit, what we call mathcal. So when we plug, when we compute the fractional Malmheden theorem at 0, we write something like this. So we can write explicitly what these objects are. We do a change of variable. We recognize polar coordinates. We change, we split these two terms and change variable in one of the two. And we recognize again the mean value theorem. So it boils, so it contains, again, like in the classical case, the fractional mean value theorem. And when s goes to 1, the fractional Malmheden theorem recovers the classical 1. And then, okay, this is essentially in words what we did, what I already mentioned. So you start with the representation of the s-harmonic function in B1 via the Poisson kernel. This produces an integral outside B1. We write it in polar coordinates. We do some scaling. We recognize the function U. So again, we do a bit of reverse engineering. And we apply the spherical change of variable at the suitable function G. And then you rearrange everything and you detect all the cancellations coming from the geometry of the problem. Okay, so it's again sort of smart computations that you have to do. There is also a fractional Schwarz theorem. So when n is equal to 2, in particular, we can have the same construction that we did for Schwarz, again multiplied by the given kernel. It recovers the classical 1. We can play the same game that we did for the temperature of the plate. Just now, the arc over the circle boundary of B1 must be replaced. I mean, it must be replaced, yes, because I have an exterior datum, so must be replaced by the cone generated by sigma. But again, I can have a geometric way to represent the solution of this problem, where now the characteristic function is the characteristic function of the cone outside, and I can do exactly the same. So let me not linger too much on this. You see, I obtain exactly the same result. Okay, so this is the proof. And maybe one final thing that I can say is that as a byproduct of Malmheden theorem and the fractional Malmheden theorem, one can actually write an s-harmonic function as the superposition of classical harmonic functions in this way. So now suppose that you have a classical problem. So for any rho, you look at UF rho to be the unique solution of the classical Dirichlet problem in the ball. So with datum on the boundary of B1 equal to this f of rho, which is of course a scaling of my original function f. Then the solution of the fractional Dirichlet problem. Now I have a fractional Laplacian of u equal to 0 in B1 with exterior datum f. Okay, so f rho was just a scaling of this function f. This can be written as a superposition, okay, an integral in the rho of the solution of the classical problem evaluated x over rho, because now I'm scaling, against the kernel. Okay, so why do we think this is nice? Because this allows us to essentially obtain a new proof of fractional Harnack inequalities, also with optimal constants, because so we know that if U is s-harmonic, you can compare basically sup and if. Okay, so U of x, you can compare it with U of 0 with constants. And these constants are optimal. Okay, so we can say that they are optimal. And for s that tends to 1, they converge to the optimal constants of the classical Harnack inequality. So basically using the superposition and together the fractional Malmheden and the classical Malmheden, knowing the Harnack inequalities in the classical case, we can recover the fractional Harnack inequality, okay, in this way. I don't have a lot of time, but basically the proof is what I said in words. So I know that for the harmonic function, I have Harnack inequality, And now it's just a matter of using this superposition. So I write u at 0 using the superposition theorem. I apply the Harnack inequality, the classical Harnack inside the integral. I rearrange things, and I recognize something here where this function g of rho t is decreasing in rho and increasing in t. And so basically you can compute the sup of this object, which is exactly the constant that we want. And so all in all, we obtain the one side of the fractional Harnack inequality. And then the other side is the same. So you use the other side of the Harnack inequality for harmonic, classical harmonic functions. And so you use again the interpolation theorem, interpolation result, the classical Harnack, rearrange things, recognize objects, and notice that basically the remaining function here would give you essentially the right constant. And, and so basically we obtain the other side of the fractional Harnack inequality. So it's a nice way to have a new proof of also of the fractional Harnack inequality, knowing the classical one. And well, we know that the constants in the fractional Harnack are optimal because we can construct a suitable example in which we have exactly equality, which looks like this. This function is s-harmonic in B1. We compute it at a given point, so we take the ratio between u of epsilon and 0, u of epsilon minus RE, E is a given direction, and then basically you compute the limit when epsilon goes to 0 of this object. This gives you exactly the right constant, and this gives basically the optimality of the constants. And I think my time is over, so I will stop here, and thank you very much for your attention.
Thank you very much for the interesting talk. Do we have any questions or comments from the participants? Elena, I can see that you unmuted yourself, but we still cannot hear you if you are speaking. You can type your question in the chat. If you have a question, there is a meeting chat. I will just put a message there. I had one question. As far as I understand, all of this work is, I mean, the fractional part is done with the fractional Laplacian, which, yes, as you mentioned, is a sort of global operator. It depends on the behavior on the whole of Rn. Can any of this be done with fractional operators that are non-local but also not global? So they depend on the behavior in some region, but not on the whole of Rn.
So like the what I would call the spectral fractional Laplacian, because so there is another version of fractional Laplacian, which is, okay, I integrate only over, say, omega. Okay, so it's like I think it's called a regional fractional Laplacian. It sees the domain. I think the first thing that one has to check is that one has a I would start with the mean value formula, right? Because Malmheden is then a more complicated construction that boils down, if you pick the center of the ball, to the classical, to the mean value formula. So I would say if there is a classical, if there is a mean value formula, and also the other thing that we use is that the knowledge of the Poisson kernel, right? To somehow reconstruct the solution. Because you have to, we do this reverse engineering proof, right? So we start with basically you start with the Poisson, the solution written using the Poisson, and then you go towards Malmheden or the other way around. So probably if you have knowledge of these things, it can be done. There is also another, let's say, less non-local fractional Laplacian, which is the spectral one. So this is what I mentioned was the regional one, okay, when you integrate over omega. There is also the spectral fractional Laplacian, where you basically look at, okay, domain omega, look at the eigenvalues of the classical Laplacian in the domain, and then you basically define the fractional Laplacian using the basically powers of the fractional powers of the eigenvalues. And then again, this is what I would call the spectral fractional Laplacian, because you use the spectrum of the Laplacian. So again, if you have, the first thing I would check is, okay, is there a mean value formula for that? Because otherwise, I mean, Malmheden is the next step, I would say. But yeah, I mean, I know that there are works also in the classical case where people have looked at mean value formulas for different operators, different local operators, and it depends a bit on the structure of the operator. So it's possible that it can be done also in other settings.
Okay, thank you. We have also a question in the chat from Elina Shishkina. She says, hello, thank you for the talk. Please tell me, do you consider iterated Laplace operator or the case when s is greater than 1?
Okay. So yes, so we haven't done anything of this in this case, because I think so when s is larger than 1, you can define the fractional Laplacian. You even have some sort of integral version where here, instead of this kind of second order increment, you go to the next order, okay, to somehow match the order of s. I don't know, because I think on the ball, so it becomes a bit trickier when s is bigger than 1, like everything becomes a bit trickier. One, because of course the expression of the fractional Laplacian is more complicated, but also because you somehow lose, in general, you lose the maximum principle, not the positivity of the operator. Maybe, I think you have some maximum principle in the ball, so you can say things in the ball. You should have a nice way to write the solution. Otherwise, I am not sure. So I don't know if one can do, for instance, a Kuran type theorem or things like that. I haven't looked at that, so I don't know much about the higher order version in this set. Definitely, we haven't looked at Kuran or Malmheden theorem.
Sorry, I was muted for a moment. Thank you for the reply. There was another message from Elina Shishkina in the chat. She just said, there is a fractional Laplacian for s greater than 1. Professor Stefan Samko has done it. See Samko Kilbes-Marichev. Yeah.
No, definitely there is. Definitely there is a fractional. You can define a problem in different ways. Definitely there is a fractional Laplacian when s is larger than 1. I don't know if, everything that I said today can be done when s is larger than 1. Because I think I see, I've looked a little bit at these things with maximum principle. So I know that, you don't have good maximum principles in general domains. You have good things only in balls. So this may make things more complicated. I don't know. But yeah, definitely there is a fractional Laplacian when s is larger than 1. One can define it and do things, definitely.
Okay, thank you. Do we have any other questions, comments? I saw someone else was typing in the chat, but didn't send any message yet. You can also unmute and just ask directly by voice. Now there is a new message from Gustavo Dorego. Professor Dipierro, thank you for the beautiful talk. In your fractional Malmheden theorem, you decomposed the non-local s-harmonic function into a superposition of weighted classical harmonic functions. Do you think this Malmheden superposition technique relies strictly on the pure power law structure of the fractional Laplacian, or could it be generalized to operators with heavier or tempered memory kernels?
Okay, to more general kernels. Okay, so here, to prove that superposition, we heavily rely on the representation formula via Malmheden theorem. Okay, so, and again, Malmheden heavily relies on the fact that you have somehow a Poisson kernel or something to start with. So, again, I would look, like if you want to do a more general operation, I would look if those basic things are somehow there. So do you have a mean value formula? Do you have for that operator a Poisson kernel? Do you have things like that? Because then if you can redo Malmheden, I think you can do things like that. So the fractional Laplacian is special in the sense that when S is 1, we recover the Laplacian. Okay, so that's why we can play this game. I don't know. I would need to look at the details of the specific setting.
I may also add something to that, since this question specifically mentioned tempered kernels. It can be that if there is a operator which is closely related to the original operator, for example, just a weighted version of the fractional Laplacian, then maybe one could extend the result using some relation with the more classical. I mention this because I'm familiar with the work of Gustavo Derrega, and I think he is working on these weighted and transmuted operators. So maybe the transmutation relations could be used to deduce the result for a different operator from the ones that are already known.
Okay, yeah, no, yes, yeah.
As I think you use the classical theorems in your proof of the fractional theorems, if I understood correctly in your talk.
Okay, so here, now I would have to, so for instance, for Kuran, okay, Kuran is another, Kuran is to say that the fractional mean value formula characterizes domain. Here we use, if I remember, we couldn't do the computations with this modified Poisson kernel, so we had to use this fact that all functions are locally s-harmonic, which I think it may be true also for other non-local operators. If one knows enough, regularity theory, because for instance, it's true. For instance, for Caputo function is always true. Is also true. So given a function, I can find a function. So I have this density result also for Caputo derivative. Next to a given function, I can find a function that is Caputo derivative equal to 0, and that is close to my original function in a suitable norm. So maybe this one is also something that can be done also for more general operators. And then Malmheden is essentially, I mean, the proof is really essentially this. Okay, so replacing the spherical averages from the classical case with the weighted, the bypassing the polar coordinates, and guessing basically the right kernel. Okay, the right, what I call mathematically this kernel.
Yeah, yeah.
So, yeah. We haven't looked like ourselves at other operators, at other situations. We were very surprised in the beginning, to discover that there is this theory, which is nice, that we didn't know much about. So we thought maybe we can try to do it for the fractional Laplacian. But then, of course, yeah, it opens up a bit of the questions in other directions.
Yeah, I think all of the questions today after this talk have been about modifying the result to other sorts of fractional operators, which, yeah, I mean, it opens up a whole new vista of questions when you do something new like this.
Yeah.
So thank you.
Even for the classical case, I think, and even just for the mean value formula, I mean, there is a lot of work that has been done, and things are not trivial at all. So, I mean, I think it's a nice problem. It's a nice topic to look into here.
Yes, yes, definitely. Okay, thank you again for the talk and the discussion. Do we have any more questions or comments from the participants?
I can stop share. Okay.
If not, then yes, once again, we thank you for the talk, and I think we can stop the recording.